Hi guys, welcome to this video where I'll be going through the Chapter 5 practice test. Do note that the practice test here is going to be slightly more difficult than the actual test. So if you understand this well, then you should be good for the test. Start with question 1. It tells us that cotangent is equal to 7/4 and sine x is less than 0, and so we need to find cosine x. Here we should probably use some kind of trig identity. A good first step is to convert this into tangent. So tangent is the reciprocal of cotangent. And the reason I chose tangent is because if we know tangent, then using an identity that can give us secant. And secant will give us cosecant. So that's a little less cumbersome than starting out with cotangent. Okay, so we have the formula 1 plus tangent squared equals secant squared. So that tells us that 1 plus 16 over 49 equals secant squared x. And so secant squared x equals 65 over 49. All right, and so that means secant x is equal to plus or minus square root of 65 over 7. And then cosine is the reciprocal of secant. So that means cosine x equals plus or minus 7 over 65, which is equal to plus or minus 7 root 65 over 65. All right, now we have to use the fact that sine is less than 0. And so if tangent is greater than 0 and sine is less than 0, then because tangent is equals to sine over cosine, then that means cosine must also be negative. And so we have to choose the negative version here. All right, and so that means that the final answer is cosine x equals negative 7 root 65 over 65. Okay, and so, when we take the square root, make sure that we're always doing a plus or minus. Make sure to account for both solutions. All right, let me show the other way to do this without converting to tangent. So this would use the fact that, so let me write another way. This way would use the fact that 1 plus cotangent squared equals cosecant squared. Okay, so that means cosecant squared equals 1 plus 49 over 16, which equals, 65 over 16? And so that means cosecant x would equal, all right, we know it has to be negative because sine is negative. And so cosecant x would equal plus or minus 65 over 4. And we're going to want to include the negative value only. So sine of x would be negative 4 root 65 over 65. Right? And then we would use the fact that cosine x is actually just equal to cotangent x times sine of x. Because cotangent is cosine over sine. And so that tells us that cosine is equal to 7/4 times negative 4 root 65 over 65, which is equal to negative 7 root 65 over 65. All right, and then, so that's the second way. A third way would have also been to start with this sign and then use the formula, right? Or use cosine squared equals 1 minus sine squared, right? But that's a different way. Let's do question 2a. Verify this identity. So if you know the cosine double angle formulas, one way you could just straightforwardly do this is just to say, this is just cosine 2x on the left side and cosine 2x on the right side. But we're going to do it not that way. Instead, what we're going to do is, we want to make the left side turn into the right side. So I'm going to make this substitution. Substitute sine squared equals 1 minus cosine squared. That's something we know from the Pythagorean identity. And so the left side becomes cosine squared minus sine squared, cosine squared x minus 1 minus cosine squared x, if we make that substitution. And so this simply becomes cosine squared x minus 1 plus cosine squared, distributing those minus signs, which is simply 2 cosine squared minus 1. And that completes the proof. Moving on to the next one. Here, the left side looks more complicated, so we should probably simplify that. So I'm going to try to get a common denominator. So we're going to do cosine x minus 1 over cosine x minus 1 times 1 over cosine x plus 1 plus cosine x plus 1 over cosine x plus 1 times 1 over cosine x minus 1. Okay, and so once we get that, we now have two denominators that are the same, and so we're able to add the numerators. And so the numerators are just cosine x minus 1 plus cosine x plus 1, and the denominator is cosine x minus 1 times cosine x plus 1. So the numerator simplifies as 2 cosine x, the minus 1s cancel out, and then the denominator is a difference of squares. So the denominator becomes cosine squared x minus 1. All right, but here we can make the substitution, right? 1 minus cosine squared x equals sine squared. And so that must mean that cosine x minus 1 equals negative sine squared. And so we're able to substitute negative 2 cosine x over sine squared. Right, the denominator is simply equal to negative sine squared. All right, so that's the left-hand side. And how can we make the right-hand side match that? Well, if we convert the right-hand side into sines and cosines, then we get negative 2 times 1 over sine x times cosine x over sine x. And that simply becomes negative 2 cosine x over sine squared x. And that completes the proof. All right, this one's a little tricky. We have a fraction, and we might be tempted to simply multiply both sides by 1 minus cosine x, but that would not be allowed. Okay, not allowed to multiply both sides by 1 minus cosine x. So instead, the only thing we're allowed to do when we're trying to verify identities is to simplify both sides. And so on the left-hand side, we're going to use the trick of multiplying by the conjugate of the denominator. All right, remember that trick? All we do is multiply the denominator by itself, except with the sign changed. So the minus becomes a plus. If it were a plus, that would become a minus. And we do that in order to introduce a difference of squares, which allows us to simplify within identity. All right, so the left-hand side, we're going to rewrite as secant x minus 1 over 1 minus cosine x. But then we're going to multiply top and bottom by 1 plus cosine x. Okay, so the top becomes secant x minus 1 times 1 plus cosine x. But the bottom is simply difference of squares, right? So this becomes 1 minus cosine squared x. All right? And so the top, now we can expand this. The top we can expand becomes secant x plus secant x cosine x minus 1 minus cosine x. And then the bottom becomes sine squared. That's using the Pythagorean identity. All right. So now, if you'll notice on the top, this is simply equal to 1. And so that will cancel out with the minus 1. And so we're left with secant x minus cosine x over sine squared x. Okay, now it looks like we're kind of stuck. And so, when you're stuck, a good trick is to always convert everything into sines and cosines. And so that's what I'm going to do. I'm going to convert that secant into a 1 over cosine. So this becomes, and I'm going to bring the 1 over sine squared to the outside. 1 over sine squared x times 1 over cosine x minus cosine x. All right, I think I need more space here. Go on to here. All right, and so I'm going to try to make these into a common denominator. So I'm going to multiply the cosine x by cosine x over cosine x. So this becomes 1 over sine squared x times 1 over cosine x minus cosine squared x over cosine x, which is equal to 1 over sine squared x times 1 minus cosine squared x over cosine x. But now you can notice that this is just equal to 1 over sine squared times sine squared over cosine squared. Because 1 minus cosine squared is equal to sine squared. And so now those cancel out, and we're left with 1 over cosine x, which is equal to secant x. And so that completes the proof. All right, so that was pretty tricky. I would say the major steps was to first multiply by the conjugate, and then second was to change everything to cosines here. Okay. Actually, now that I think about it, there's also an easier way. I'll do over here another way. What you could have also done is simply convert the secant to a 1 over cosine as the first step. Does that work? Yeah, that's actually a much easier solution. So what you could have done is simply written this as 1 over cosine x minus 1 all over 1 minus cosine x. Okay, but then that numerator is actually simply, if we rewrote this, this is actually just equal to 1 over 1 minus cosine x, that's the denominator there, times 1 over cosine x minus cosine x over cosine x. And so actually, everything cancels out. And we're left with just 1 over cosine x, which is equal to secant x. Probably a much better solution. Unfortunately, I didn't see that the first time around, which was rather foolish. Okay, let's keep going. Okay, so trying to solve this or verify this. So the first step, I'm noticing that this is just a cosine squared. And the left side, I'm probably going to want to convert to sines and cosines. Okay, so I'm going to do the right side first. The right side is just cosine x over sine x, because 1 minus sine squared is cosine squared by the Pythagorean identity. And then the left side, I'm going to convert to sines and cosines. So this is just 1 over 1 over sine x times cosine squared x over sine squared x. All right. The reason is because cosecant is 1 over sine, and cotangent squared is cosine squared over sine squared. And so this simply becomes sine x times cosine squared x over sine squared x, which is equal to cosine squared x over sine x. And we're done. Okay, so notice how I've split up the left-hand side and the right-hand side. That helps a lot with the clarity of your presentation. Next one. Okay, so we have an addition of two fractions, which means that we should get a common denominator first. And so I'm not going to show it out entirely, but essentially we just cross multiply and add those in the numerator, right? So that becomes cosine x minus cosine y times cosine x plus cosine y plus sine x plus sine y times sine x minus sine y. And that's all over sine x plus sine y times cosine x plus cosine y. All right, so in the numerator, that allows us to expand. Actually, these are both differences of squares. And so this becomes cosine squared x minus cosine squared y plus sine squared x minus sine squared y. And the denominator I'm going to leave unexpanded because it's not helpful for us. We're trying to prove that this fraction equals 0, right? And so all we care about is the numerator. Okay. But now we can notice that we can actually group these in a pretty meaningful way, right? We can group this with this, group that with that. So this is actually just cosine squared x plus sine squared x minus cosine squared y plus sine squared y all over the denominator. Which is just 1 minus 1 over that denominator. Which is just 0. Here we've used the fact that cosine squared plus sine squared is equal to 1. Okay, next one, very similar. Probably going to try to get the left side to be a 1 fraction. And so it's going to be cotangent x over secant x times cosecant x over cosecant x. Get that common denominator over tangent x cosecant x times secant x over secant x. So that will leave us with cotangent x cosecant x plus tangent x secant x Is this helpful? No, actually this is the wrong way to solve it. Very sorry. All right, sometimes we realize things don't work out. That happens. I'm realizing that the best way to solve this is actually by changing everything to sines and cosines. And so this would become cosine x over sine x, that's cotangent x, times cosine x plus sine x over cosine x times sine x. Okay, the logic here is that cotangent is equal to cosine over sine, and then 1 over secant x is equal to cosine x. Okay, and then similarly, tangent is equal to sine over cosine, and cosecant is equal to 1 over sine. That's how I got that. And so really this becomes cosine squared over sine plus sine squared over cosine. Okay? So that's the left-hand side. And perhaps now we can start working with the right-hand side, converting those into sines and cosines. This is going to become 1 over cosine x plus 1 over sine x minus sine x minus cosine x. Okay, and so the trick now is actually to group these in a kind of special way. We're going to group together the cosines and the sines. So we're going to do 1 over cosine x minus cosine x plus 1 over sine x minus sine x, in that way. And then this actually becomes 1 minus cosine squared over cosine plus 1 minus sine squared over sine. Okay, we can do that if we try to get common denominators. But then if we now use the Pythagorean identity, this leaves us with sine squared x over cosine plus cosine squared x over sine, which matches the left-hand side. Okay, so that's a little tricky. You could have done the same thing by replacing these with 1 minus sine squared and 1 minus cosine squared. You would have gotten the same result, and you would have been able to convert this into the right-hand side. But we kind of made the left and right-hand sides meet in the middle. Okay, next we're going on to solving some equations. So the first step is always to, for these simple ones, we want to isolate the trig function. So this becomes cosecant x equals 2 over root 3, which means that sine x equals root 3 over 2. Right? Because sine is the reciprocal of cosine. And so that means we're looking for points on the unit circle with y-coordinate root 3 over 2. That's here and here. So that means x equals pi over 3 plus 2 pi n and 2 pi over 3 plus 2 pi n. All right, remember we're adding 2 pi n because the period of the sine function is 2 pi. And so we want to account for those infinite sets of solutions, sets of infinite solutions. Next one. This tells us that tangent x equals root 3. And so here we actually only need one solution because the period of tangent is pi. So the other solution will automatically be accounted for when we add pi n. And so the point in the one point is one point of the unit circle such that tangent equals root 3 would be that point there, pi over 3. And so that tells us that, let me label these. All right, the other point would have been, what is that, 4 pi over 3? But that's already accounted for in the fact that the period of the tangent function is pi, right? Because that's pi over 3 plus pi. And so our final answer is x equals pi over 3 plus not 2 pi n, but pi n. Next question. This has us solving, all right, solving for x. And so in this case, we're going to write things as a quadratic. So this is equivalent to 2y squared plus y minus 1 equals 0. So we're going to factor by grouping. We're looking for two numbers that multiply to -2 and add to 1. -2, right? A times c. 1 is the b term. And so that's 2 and -1. Which factors as okay. So that means we can plug this back in, plug back in y equals cosine x. Now we have 2 cosine x minus 1 and cosine x plus 1. All right, so splitting that up into two cases, either we have cosine x equals 1/2, or we have cosine x equals -1. And so on the unit circle, that corresponds to this point and this point, right? That's 1/2. Cosine x equals 1/2, x coordinate 1/2. That's pi over 3, 5 pi over 3. And then for cosine x equals -1, that means that the x coordinate is -1. So that's here at pi. And so our final answer is going to be x equals pi over 3 plus 2 pi n, pi plus 2 pi n, and 5 pi over 3 plus 2 pi n. Okay. Secant x times cosine x, cosecant x equals 2 cosecant x. Here you might be tempted to divide both sides by cosecant, but that would be illegal. It would lose you some solutions. Let me write a reminder. Do not divide by cosecant. Okay, instead, what we have to do is factor by moving all the terms to the left side. So this becomes secant x cosecant x minus 2 cosecant x. This allows us to factor out a cosecant x, and we're left with secant x minus 2. And those multiplied together equals 0. That means we split it up into two cases. Either cosecant x equals 0, or secant x equals 2. Okay. But that cosecant x equals 0 is actually impossible, because cosecant x equals 1 over sine x, right? And so it's actually impossible for cosine to equal 0, because that would mean sine x would have to be infinite, which doesn't happen. Okay, but if secant x equals 2, that simply means that cosine x equals 1/2. And so that corresponds to pi over 3 and 5 pi over 3. And so our solutions are x equals pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. Next one, cosecant x plus cotangent x equals 1. So for this one, what we're going to have to do is square both sides at some point, but there are different ways you could do it. Okay, let me show you the first way. Firstly, what we could do is move the cotangent to the right side and then square both sides. Okay, it doesn't work if you just immediately try to square both sides. The reason is because you'll encounter some cross terms. You'll encounter terms like 2 cosecant x times cotangent x, which makes things more complicated. We want to move things such that each side only has one trig function. So the left side becomes cosecant squared x equals, and the right side becomes 1 minus 2 cotangent x plus cotangent squared x. And here we're going to use an identity. We're going to use the fact that cosecant squared equals 1 plus cotangent squared. This becomes 1 plus cotangent squared equals 1 minus 2 cotangent x plus cotangent squared x. Right sides stay the same, but then everything cancels out and we're left with just 0 equals negative 2 cotangent x, or cotangent x equals 0. All right, and so on the unit circle, the point that corresponds to that is simply going to be this point and this point. Okay. Actually, it's very important that you include both points. In cases such as these, it's not okay just to choose one and then just to say, oh, plus pi n. The reason is because this point and this point give you different values of cosecant. They give you the same value of cotangent, but different values of cosecant. And so actually, when you plug them back in, which you have to because you need to check for extraneous solutions because we squared both sides, when you plug them back in, they're going to give you different values. And so both of them need to be included in your answer, even at this stage. And so we're going to say, this tells us that x equals pi over 2 plus 2 pi n and 3 pi over 2 plus 2 pi n. Okay. And then we need to plug both solutions in because we squared both sides, so that will introduce extraneous solutions. Well, indeed, when we check these solutions, we're going to find that cosecant pi over 2 plus cotangent pi over 2 equals 1, so that's good. But cosecant 3 pi over 2 plus cotangent 3 pi over 2 is actually equal to -1. And so that's not correct. And so the final answer is only pi over 2 plus 2 pi n. And 3 pi over 2 is discarded. Okay, so that's the first way of doing it. Let me show you guys another way. Suppose now instead we moved the cosecant to the right side. That would give us cotangent x equals 1 minus cosecant x. And so squaring both sides, we're going to get 1 minus 2 cosecant x plus cosecant squared x. Okay, now converting the cotangent squared to cosecant squared minus 1. That becomes this. So these cancel out. And we're left with -2 cosecant x equals -2. And so cosecant x equals 1, which means that sine x equals 1. And so that gives us only that point, which means that x equals pi over 2 plus 2 pi n. And we've already verified that, right? But I'll write it again. Okay, so that's another way of doing it. Let me show you guys yet another way. We could have also converted both the cosecant and the cotangent to sines and cosines. Now multiplying both sides by sine, that leaves us with 1 plus cosine x equals sine x. All right, that's technically a bad step because it introduces some extraneous solutions, but we're going to ignore that for now. Okay, then we square both sides. And then rewrite that sine squared as a 1 minus cosine squared. So this is going to turn into, right, the 1's cancel out. So we have two cases, cosine x equals 0 or cosine x equals -1. That corresponds to these 3 points. So x equals pi over 2, or pi, or 3 pi over 2. But then if we plug things back in, we would find that only pi over 2 works. All right, there's even a fourth way, which I won't show, where you could have moved this 1 to the other side and then squared it. And then you would have solved in terms of signs. But I'm not going to show that. Okay, so hopefully it makes sense. We always need to check for extraneous solutions. There was only one solution that did not yield an extraneous solution. Okay, but in the end, after we eliminate those extra solutions, we're going to get the same answer. Okay, next, we want to isolate that tangent, right? And so 3 tangent x over 2 equals root 3. And so tangent x over 2 is equal to root 3 over 3. All right, so what point does that correspond to? That is going to correspond to this point here. Right, that's going to have coordinates root 3 over 2, comma 1/2. And so that tangent is 1 over root 3, or root 3 over 3. And so that means that x over 2 is equal to pi over 6 plus pi n, right? Remember, the period of tangent is pi. And so solving for our x, that tells us that x equals pi over 3, multiplying both sides by 2, plus 2 pi n. Next, we want to solve for x. Here, we're going to want to use a a Pythagorean identity. There are different ways you could do it. You could either convert the secant squared to a tangent squared or tangent squared to a secant squared. Let's do the first way first. Convert the secant to a tangent. So we're going to use the fact that secant squared equals 1 plus tangent squared. So this becomes 2 plus 2 tangent squared plus tangent squared minus 3 equals 0. If we simplify, that gives us 3 tangent squared equals 1. All right, 3 minus 2. So that means tangent squared equals 1/3, or tangent x equals plus or minus root 3 over 3. All right. And so on the unit circle, that corresponds to here and here. And so x equals pi over 6 plus pi n, or 11 pi over 6 plus pi n. Those would be our two solutions. You could have also written or negative pi over 6 plus pi n. But that's the same thing as 11 pi over 6. All right. So let me do another solution. Let's say we converted that tangent squared into a secant squared. This would become 2 secant squared x plus secant squared x minus 1 minus 3 equals 0. So that would tell us that 3 secant squared equals 4. And so secant squared x equals 4/3, which means that secant x equals plus or minus 2 root 3 over 3, which tells us that cosine x is equal to plus or minus root 3 over 2. That is going to give us the exact same set of solutions. Right, looking for those points with x coordinate either positive root 3 over 2 or negative root 3 over 2. Tells us that x equals pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6 plus 2 pi n, 11 pi over 6 plus 2 pi n. And these are the exact same group of solutions as the left-hand side. All right, next. Sine squared equals 3 cosine squared. Now, what you could do is divide both sides by cosine squared, but we always want to avoid doing that because that could lose some solutions. We might accidentally omit the cases in which cosine equals 0. Thankfully, that's not any one of the solutions, so if you did that, you would have gotten the right answer. But it's a generally bad practice because it causes us to lose solutions most of the time, or sometimes. Instead, what we're going to do is convert to sines and cosines, or convert to only sines or only cosines. Here I'm going to use the fact that sine squared equals 1 minus cosine squared. So that will leave me with cosine squared equals 1/4. So cosine x equals plus or minus half. All right. So on the unit circle, that's here, 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 and here. Points with x coordinate, either half or negative half. It's pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay. Another way of doing this would have been to write cosine squared as 1 minus sine squared, and you would have gotten the same thing. Sorry. Okay, next, tangent 5 pi over 12. This is going to require us to use some kind of tangent addition formula. And so we have to be quite clever here and think about which two angles that we know tangent for, which two angles would give us 5 pi over 12. And so there are different ways of doing this. But personally, what I would do is use, what would I do? Pi over 6 plus pi over 4. Okay, so how I got that? I figured out that 5 pi is just equal to 2 pi plus 3 pi, which is equal to pi over 6 plus pi over 4. So that means I can use a tangent addition formula. All right, remember, tangent x plus y equals tangent x plus tangent y over 1 minus tan x tan y. Make sure to get those signs right, especially don't forget the minus sign in the denominator. So that is going to come out to root 3 over 3 plus 1 all over 1 minus root 3 over 3 times 1. And if we multiply top and bottom by 3, then this becomes root 3 plus 3 over 3 minus root 3. Here we have to rationalize, right? Don't forget to rationalize. By rationalizing, we have to multiply the denominator by its conjugate. So the top is going to become 9 plus 6 root 3 plus 3. All right, I just use a squared plus 2ab plus b squared. You can confirm with FOIL. And then the bottom is going to become 9 minus 3, just by difference of squares. So that leaves me with 12 plus 6 root 3 over 6 equals 2 plus root 3. Okay. You could have also done 5 pi over 12 equals 8 pi minus 3 pi, which is 2 pi over 3 minus pi over 4. Okay, another way of doing it, equally valid. And then you would have used a tangent subtraction formula instead. Let's do the next one. Verify this identity. So this clearly requires us to use a cosine subtraction formula to simplify that left side, right? So we're going to do that. The left side is equal to, right, remember that cosine x minus y equals cosine x cosine y plus sine x sine y. Right, when it's a subtraction formula, you have a plus in the cosine. So this becomes okay. Now cosine 5 pi over 4 is equal to negative root 2 over 2. But sine 5 pi over 4 is also equal to negative root 2 over 2. And so if we factor both of them out, we're just left with cosine x plus sine x, which proves the identity. Next one is the same concept. We're going to use the cosine addition and subtraction formulas. So this is going to become, now if we expand this, we're going to get this is just a difference of squares actually. So we get cosine squared x, cosine squared y. This is not as straightforward as I thought it was. Is this even true? This is not even true. This is not valid. This is not what I was trying to do. I think I made a typo in the question. Must be. Oh no. Yeah, I did. This is supposed to say sine squared y. Okay, that's not good. Okay, I'll change that in the file. Okay. That is more sensible. But still. How do you prove this? Well, clearly we want to get rid of the cosine y and the cosine... Sorry, we want to get rid of the cosine y, and we want to get rid of the sine x, because those don't appear on the right-hand side. So it's a good idea to make some substitutions here. Okay, so let me indicate that with some colors. Okay, so after we expand it, we get that expression. But then the magical thing is that this and this cancels. And so we're left with cosine squared x minus sine squared y. Okay, it's very tricky. That is very tricky. I'm wondering if there's an easier way of doing it, but I can't think of any. Okay, well, yeah, okay. Question 10, solve for x. Here we're going to use a double angle formula. So sine 2x equals 2 sine x cosine x. And so this will become 2 sine x cosine x times sine x equals cosine x. In other words, 2 sine squared cosine minus cosine equals 0. Remember, we can't divide both sides by cosine. Don't divide. Not only don't, can't. The reason is because if you do that, you're going to lose those cases where cosine actually equals 0, because you're not allowed to divide by 0, right? But cosine is allowed to be 0, as we'll shortly see. After we factor cosine from both sides, from both terms, we're left with 2 sine squared minus 1. So either cosine x equals 0, or 2 sine squared minus 1 equals 0. But that means that sine x equals plus or minus root 2 over 2. Okay. And so we're left with these solutions on the unit circle. Okay, for cosine x equals 0, we have this solution and this solution. It's pi over 2 and 3 pi over 2. And then for sine x equals plus or minus root 2 over 2, that means that we are looking for y coordinates of plus or minus root 2 over 2. So that's here, 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 and here. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. All right, so in total, we actually have 6 solutions to this equation within 0 and 2 pi. And so we would write our answer as x equals pi over 4 plus 2 pi n, pi over 2 plus 2 pi n, three pi over 4 plus 2 pi n, 5 pi over 4 plus 2 pi n, 3 pi over 2 plus 2 pi n, or 7 pi over 4 plus 2 pi n. Or you could have also written x equals pi over 4 plus pi over 2n and pi over 2 plus pi n. That's another way of writing the same exact thing, because all of these solutions are separated by pi over 2, right? Whereas the pi over 2 and 3 pi over 2 are separated by pi. All right, and there are no extraneous solutions here because we didn't do any bad or illegal steps. We didn't multiply both sides by anything. We didn't square both sides. So we're all good there. Okay, final question, power reduction. All right, so as my first step, okay, so let's first recall the power reduction formulas, right? Sine squared equals 1 minus cosine 2x over 2. And cosine squared equals 1 plus cosine 2x over 2. Okay. My first step is that I'm going to rewrite this in terms of sines and cosines. That helps get rid of a power of 4 at least. You could have just straight away applied the tangent power reduction formula, but I think that would take more time. All right, so we are left with sine squared times cosine squared. And now we can just plug in our power reduction stuff. That will leave us with okay? And then we can plug in another power reduction formula, simply in this case with the 2x replacing the x. In other words, cosine squared of 2x is equal to 1 plus cosine 4x over 2. And so that means this is equal to 1/4 minus 1/4 times 1 plus cosine 4x over 4. Which leaves us with 1/4 minus 1 over 16 minus 1 over 16 cosine 4x, which is 3/16 minus 1/16 cosine 4x. And we would be done. All right, maybe I'll show you the other way, just for fun. All right, we also know that tangent squared 2x is equal to sine squared over cosine squared, so that would be 1 minus cosine 2x over 1 plus cosine 2x. So another way of doing it would be to do right? But then you should notice that a lot of things cancel out. And we're just going to be left with 1/4, right? Because we have a 1 plus cosine 2x squared here and a 1 plus cosine 2x. So this just leaves us with 1 minus cosine 2x times 1 plus cosine 2x, which directly goes to there anyways. Okay, so that finishes this video. Remember that the real test will be a little easier than this. I know this is a pretty hard practice test, but hopefully this gives you a good practice with some harder questions.